last case that we're going to cover, we're going to be looking at a single pass versus a partial two-pass seawater system. And we're going to be just comparing both and seeing what the benefits of both are in this design. So in this case, we're going to be using it would be a plant in Egypt with an open intake seawater of SDI less than 5. And we're also going to be using a UF pretreatment. Feed salinity is approximately 42,000 milligrams per liter. Feed boron of 5.5 milligrams per liter. Feed pH of 8. Operating temperature between 18 to 32 degrees. Production of 30,000 cubic meters per day. Recovery between 45% to 90%. Maximum membrane age of 3 years. Permeate TDS requirement of 350 ppm. Chloride requirement of 200 ppm and boron requirement of 2.4 ppm. We're also going to want to operate with 5 trains. There's no N-1 trains requirement, however, so we just need to make sure our number of pressure vessels is divisible by 5. Additional notes, we're going to again include an energy recovery device with pressure exchanger with a 6% volumetric mixing. And as mentioned, we want to consider 2 options. We want a single pass seawater design, and we also want a partial 2-pass design. And with the partial 2-pass, in this case, the requirement would be we can only use a simple split. So let me switch again back to Q+. So again, we have another tab open with our feed salinity already added in. So in this case, 42,000 milligrams per liter. We'll hit balance and save. For your feed source, this is an open intake system with SDI less than 5. This is an open intake system. However, with UF pretreatment, we can go from SDI less than 5 to SDI less than 3. So in this case, we'd select seawater well. One thing we did want to add in was our energy recovery device. So isobaric, and with 6% volumetric mixing. We'll save that. And then let's change the temperature to the maximum, just 32 degrees. Feed pH of 8. Membrane age of 3. Permeate production of 30,000 cubic meters per day. Recovery, it was 45% and 90%, so 90% would be for the second pass if we had it. In this case, we're going to be starting with our single pass design, so let's just do 45%. So for number of elements per pressure vessel, let's again do 7. For your membrane selection, let's start with GR again, and then if we need a tighter membrane, we can go to SR, and if we need a looser membrane, we can go to R. And for number of pressure vessels, let's choose something. In this case, because we do have a open intake with UF pretreatment, the flux is a little bit higher than an open intake system. However, it's not quite as high as a beach well system because even with UF pretreatment, the fouling potential is slightly higher than a beach well's water source. So in this case, let's choose a system flux somewhere around 14 LMH, let's say. So if we want to target 14 LMH, let me just choose a number of pressure vessels, 100, and then we see the average flux is around 44. So we do need to increase this. Let's try 300. So that's around 14.5 LMH. That's still a little bit higher than what we want. We want to get it down to closer to 14. So let's go to 310, for example. So at 310, we're at 14.1 LMH. This is basically around what we're targeting. So that could be acceptable. And we'll calculate. And we know the permeate TDS requirement of 350 ppm. So we're meeting that. Permeate chloride of 200 ppm, and we're at 191. And the permeate boron requirement of 2.4 ppm, and we're at 1.3. Right? So we are meeting all the permeate quality requirements. But again, maybe safety margin is something that you want to consider. So if you are concerned, if you do want to consider a safety margin, let's just say you want to consider a 30% safety margin again, right? So in this case, a 30% safety margin, chloride is your most limiting factor right now because the permeate TDS at 350, chloride's at 200, and then boron is at 2.4. So we can see here that chloride is the closest to the limit. So chloride at 200 ppm, with a 30% approximately safety margin would be about 154 ppm. So we want to target around 154 ppm. So in this case, the chloride is at 191, so let's change this to a tighter membrane. So in this case, we'll go from GR to SR and calculate. And now we'll see, okay, now the permeate chloride is right under 154 ppm at 152 ppm, right? So this could be acceptable for your single pass design. And again, another thing we do want to check is the maximum feed pressure. So at 18 degrees Celsius, we'll note the maximum feed pressure of approximately 74.2 bar. Okay, so let's just say this is acceptable now for our single pass, one pass seawater design. We want to open up a second one because now we want to check a partial two pass design. So the water profile, again, we need to enter the water profile information. I'm going to go to the drop down and select our case study 3, our feed source, seawater well. Our units, I'm going to be changing this to meters cubed per day, selecting the maximum temperature, membrane age, 45% recovery. Because it's a partial two pass, we're going to add in that second pass. 90% recovery in the second pass. And approximately 33,333 cubic meters per day to get 30,000 total production. We're going to change the second pass membrane age as well to 3 years. Add in the second stage for the second pass. In this case, let's select our membrane again. Let's go with the BWES, which is our energy saving brackish water membrane. 7 elements per pressure vessel. Add in our isobaric exchanger with 6% volumetric mixing. Add in our brine recirculation. We're going to change this to percent again, and we're going to use 100%. Okay, so our first pass model, let's select. So we do have, as I mentioned, SR, GR, R, and ES. In this case, let's go with R because we are choosing a looser membrane than our single pass design for the first pass. So we'll go with R, and then now let's adjust the number of pressure vessels in order to get approximately the flow we need. So we were targeting around low 14 LMH. So in this case, let's start again around 300 and see where we're at. So 16 is quite high. In this case, let's increase to 310 as we did previously. We'll notice the flux is still quite high at 15.7 LMH. So let's go to 330. Still a little bit high. So let me change this to 350. And so that's right under 14 LMH. Okay, so that's acceptable in this case. And for a second pass, we want to change the number of pressure vessels as well. Again, we want to keep these divisible by 5 because we do have 5 trains. Let's try 100. And let's try 35. So we calculate first. So keep in mind our permeate target was, permeate chloride target was around 154 ppm with our safety margin. In this case right now, when you have a full two pass system, the permeate chloride will be less than 6, right? So obviously we have plenty of room for a permeate split. So we can also reduce the number of pressure vessels in the second pass as well when you add this permeate split. So let's just do it by percentage, and then let's try somewhere around, let's just say 50% first. So let's adjust the number of pressure vessels in the second pass as well. Let's go 50 and 20. Okay, we'll see here our permeate chloride, instead of 154 ppm was around the target, now we're at around 130 ppm, so we do have room to increase. Let's try increasing this from 50% to, let's say, 60%. Okay, so we're right under 154 ppm now when we have 60%. However, we do still want to change our second pass number of pressure vessels because of the flux. We need to change the production. And once the production changes, maybe the flux for the first pass will drop. So maybe that would affect our number of pressure vessels in the first pass as well, right? So we do want to make sure we keep these things in mind when we do make changes. So we change the production in the first pass. Now you'll see the first pass flux is, instead of close to 14, it's at 13.14, right? So let's reduce this. Try to around 320 ppm or 320 pressure vessels. So now you'll see the average flux is a little bit higher, around 14.4. Maybe we want something around 330 or 325. So let's say 325 is good because now we have average flux around 14.1 LMH again. In our second pass, we want this average flux to be between 30 to 34 LMH. So maybe we can reduce this. Let's just try 40 and 15. So we do have a little bit more room. We're at 30 LMH. So let me change this from 40 to 35. So we're going to calculate again. Now you'll see your permeate TDS. The target was around 154 ppm chloride. So maybe we do have a little bit of room. And also you'll notice that we do have a high flux warning in the second pass. So maybe that means the flux is a little bit too high. So let's increase this from 60% to 62%. And then now let's recalculate the flow that we need. So in this case here, you can see now, okay, we're at 157 ppm chloride. Maybe that's a little bit too high because we were targeting 154. So maybe instead of 62%, we want to go to 61%. Another thing is our first pass, now it's under 14 LMH. Maybe we wanted a little bit more. So let's change this to from 325 to 320. And again, now we're at about 14.2 LMH, right? So we recalculate that with a higher flux, and maybe now this will be more acceptable. So right now we're at right about 154 ppm chloride. So maybe now this is an acceptable design. So we are meeting the worst case permeate chloride, permeate TDS, and permeate boron. Another thing that we do want to check, of course, is our feed pressure. So our feed pressure at minimum temperature would be 18 degrees. That would be the maximum feed pressure. So you'll notice now that we have about 65.2 bar. For a maximum feed pressure, compare that to the previous case when we only had a single pass design. If you calculate that, you'll notice we have 74 bar, right? So you're going from 74 bar down to around 65 bar. That's approximately a 9 bar feed pressure savings in terms of the worst case conditions. Even at 18 degrees, for example, you'll note that the permeate chloride is still in the first pass is less than 184 or 154 ppm, excuse me. Because it's still less than 154 ppm, what this means is we can actually operate the two-pass design as a single pass at 18 degrees and potentially higher, right? So basically, we want to see at what point do we go do we hit approximately 154 ppm chloride, right? So let me just change the temperature. Let's go to 24. We calculate it again. You'll see our permeate chloride is now right under 130. So we can go a little bit higher. Let's just check 120, or let's check 26 degrees. So 126 degrees, or at 26 degrees, excuse me, now we're at 151 ppm. So basically what we see now is that with our partial two-pass design, we do need the two passes, the partial second pass at the maximum temperature. However, you can operate with a single pass only up to temperatures around 25, 26 degrees, for example, and you can still meet the quality in a single pass, right? So if it's at 26 degrees or below, we can just not use the second pass and operate only at a single pass. That'll of course still affect the permeate TDS if you get rid of the brine recirculation, for example. But let's just say, for example, you don't need the second pass, you can delete all of this. You'll still notice that the feed pressure at 26 degrees, for example, is still at right under 63 bar. And then if you do the same for your single pass design, you'll notice that the feed pressure right under 63 bar compared to 69.6 bar. Right? So you'll still see a large savings in terms of feed pressure when you do the partial two-pass system. Even at max temperature, even if you do have a second pass where you have feed pressure to consider, the overall energy consumption will still be quite similar for your single pass versus your partial two-pass. So let me go back to our PowerPoint. So this is approximately the designs that we came up with for our single pass SWRO and also for our partial two pass, right? Maybe there are some little changes here and there in order to, just because, sometimes they'll be a little bit different in terms of how you design each time. So both designs that we created, the single pass and the partial two pass, both of those designs meet the permeate quality requirements at the worst case conditions. So you get permeate TDS less than 350 ppm, permeate chloride less than 200 ppm, and permeate boron less than 2.4 ppm. And with the permeate chloride requirement, we still have that 30% safety margin in our design. So we're targeting 154 ppm. So we do have room on that, just in case anything happens. And we have benefits on both sides for both single pass and the partial two pass design. For the single pass design, the benefits is that you do have a simplified design and operation. You don't need to worry about starting up and shutting down the second pass depending on the temperatures. You don't need to worry about changing the split percentage, for example, depending on the requirements. You just operate at single pass at all times. You also have a reduced capital cost because you don't have a second pass. You have less pressure vessels, less membranes, less equipment, less piping. And of course, you have less space overall required for your RO plant. On the other hand, the partial two-pass design does have some benefits as well. It does have lower energy consumption at most conditions, minimum to average temperature, for example. And then even at maximum temperature, it will be similar in terms of energy consumption. So overall, you will save money in terms of energy consumption when using this two-pass design. You do also get to optimize the performance for different conditions. You'll notice the second pass only operates as needed in order to meet the quality. However, for the single pass system, even though you're overachieving in quality at minimum and average temperature conditions, because you're just based on a single pass design, that design, for example, would not have the flexibility to optimize the permeate quality. So these are just a few examples of how we begin our design process. As I mentioned, these are ongoing processes. So based on a lot of feedback, for example, with your client, or with, depending on how your priorities shift during the design stage, maybe some of these designs will still be acceptable. Maybe some of these designs need to be changed, right? So these are just good starting points in order on how we typically build our seawater systems. Hopefully you found it helpful. So thank you for attending. Now we'll be getting into the Q&A section. So if you do have any questions, feel free to ask them in the questions tab, and I'll get to those in a minute. If you have any further questions, feel free to email me at kchao, kchao @lgchem.com. Thank you again for attending, and I'll be answering questions shortly.